back up to that equation. Let's go the one right above it.
9/11, yeah.
Right, but in between 9/11 and 9/12.
Okay, this thing.
Yeah. So, okay. So, mr double dot should be 0, right?
Yeah, whenever the equilibrium, the tide has stabilized. Well, I guess we could do like a slow approximation, like an adiabatic. It's always equilibrium.
Yeah. It's always so that's 0 because we're standing on the Earth. All the inertial forces that we have to deal with are thrown into ftid.
ftid, yep.
Okay, so that means it's 0 equals mg plus ftid plus f any non-gravitational stuff.
Mm-hmm.
The mg is constant on the surface of the Earth. It's not constant because the vector's changing, but the magnitude is always the same.
I mean, the magnitude changes, but you got to be like Everest and higher, like for the oceans.
Right.
Close enough. Don't worry about it.
So essentially, at a particular point on Earth, this mg is just a vector
Constant.
quantity, never changing.
Yep.
So if you're if you need 0 plus a constant plus ftid plus fng, that means if the tidal force goes up, then the fng goes to go down, or vice versa. If f tide goes down, then fng needs to go up. So they balance each other.
Yeah.
So when you're on the closer part, like I said, let's look at this picture. Yeah, point P. ftid is at its greatest point. So that means in order to compensate, fng has to move. Why does the bulging create that change in fng?
So I'm not sure that that's the right interpretation.
Okay, I'd like to hear your interpretation.
So I think the fng is, for example, in this case, the buoyant force. So if you had like a boat sitting on the ocean, and so the buoyant force is rho vg. The density of the fluid times the volume displaced times the gravitational force. And I think that doesn't change.
Okay.
And so I think
now I'm confused.
Right. So I think the interpretation is this is equal to 0 at the high tide, like the highest high tide. In which case ftid will have scaled in order to make this equal to 0. At the point where we're, say, at not low, I guess anywhere from low tide to high tide, this thing is some positive number. It's like growing. It's the acceleration of the water is get higher. And so in order to, how do I say this? It's if this is some positive number and this is some fixed number, and then this has to be the corresponding number to grow. Oh man, that's just some garbage sentence. What I'm saying is,
but
the tidal force, like the tidal force is going. Oh gosh, which one happens first?
Well, okay, but isn't this an equilibrium? We're using this equation in some sort of equilibrium, right? And in which case, I can take a packet of water at point P, balance its forces out, and it should equal to 0. I'm not looking at it accelerating into position yet. Like it's already in position. Right? So these aren't
that's what I'm asking. Like maybe this is something not quite 0. And that's what gives it this acceleration to climb in height.
But then okay. So what stops the climbing in height then? So it's climbing. Mg is constant. F tide is towards the moon. Fng is constant. So if you're a packet of water sitting on the surface of the water, you're getting a little bit of extra nudge towards the moon. You're just going to keep going, right? What's compensating it to stop it? Surface tension? But
interesting. I see what you're saying. Is there another sweep under the rug here?
Yeah, maybe. Because I guess it's kind of a details question.
Yeah.
But I'm not seeing why the bulge is the response to the to the tidal force. Unless I fall back on that intuitive picture
Okay, so
above,
let
which you
me
said is completely wrong.
completely wrong. So let me catch up to you. What you're saying is this is a geometric factor. Like this
Yep.
is the real thing.
Okay, yeah.
Like,
Yeah.
and so just the fact that you're out here and these distances are different, that means the tidal force is going to be whatever it's going to be.
Exactly.
The response will be in the rest of the system. And if we're saying that this is going to be whatever number it is, and this is constant, then somehow the other two terms have to make this equation.
Right.
And
And
if
I
you're,
think if I'm interpreting this right, the mr double dot should be 0 because we've already put all of the the inertial acceleration that's causing the circular motion into ftid. So we're standing on the surface of the Earth. The acceleration of a packet of water as we're standing on the surface of the Earth should be 0. So the reason there's a bulge, a static bulge for a short amount of time, is FNG the water had to bulge to make a different FNG to compensate for the F tide.
but if I see what you're saying. I'm almost there. It is just on the cusp of my brain. So would that suggest that when you're at high tide or low tide, your boat sinks into different amounts of the water? But if,
No
but if the buoyant
way.
force is rho VG, the rho
Like, it's
is
not
the density is not really changing.
Right. Now, the water bulges, so there's a slightly higher buoyant force if you're deep down. But near the surface, there's no change in buoyant force.
Yeah.
So why does that water stop bulging?
You're saying
Shouldn't it just continue?
you're now switching to like
continue
a
to bulge?
vector description, like all the forces are in the same direction. Is that what you're saying?
Well, if I'm thinking if I'm at point P, and the argument is the tidal force is accelerating me towards the moon.
Yep.
If I'm on the surface of the water,
Mm-hmm.
I feel a tidal force towards the moon, so I start to bulge out.
Mm-hmm.
But as I bulge out, shouldn't I feel a resistance force so that I stop bulging?
I see what
What's
you're saying.
stopping me?
So-
What's stopping the bulging from bulging more?
Right. You're saying that because of geometry, this gets larger,
Yeah.
which makes this water bulgier.
Yeah.
But if this is constant, the gravitational force from the Earth, and the buoyant force is constant, but this is growing, like what is there another term here that makes this
What-
equal to 0?
Right. What's the compensatory force to make the bulges different? Like, I imagine if I'm got tides on Jupiter, they're going to be bigger.
Yeah.
So it needs more bulge to get the same amount of equilibration force. Which means somehow the bulge, when the tidal forces are bigger, the bulge is bigger. The bulge is somehow being created to compensate for the larger tidal forces. But I got no intuition as to why the bulge is necessary to do that. This is probably just details. Right?
No, I don't know. Thought I had
don't-
this.
I thought I like the vector picture,
Yeah, seems good.
but I'm a little lost on what stops the bulging from bulging. Is it the mg? Like you're literally getting farther from the Earth? No, it's such a small amount.
It's such a small amount because we see from observation that the height of the tide is like a meter or something. Is that right?
Yeah, it's not much.
So like not much at all.
Right, and it's even in the wrong direction at point P, because the tidal force is towards the moon, and then if you move away from the center of the Earth,
You get a weaker gravity.
you get a weaker gravity, so that's in the wrong direction.
It's in the wrong direction.
And I guess for circular motion, the non-inertial part, I'm thinking of centripetal acceleration, because I'm closer. but I'm going slow. So as I get closer, now I'm lost.
If you have a fixed velocity, a fixed angular velocity, or linear velocity, and you go closer, then you get pulled harder. But exactly as you said, like the Earth, the near side of the Earth doesn't have to go around as fast. I guess it has a fixed, it has a fixed angular velocity.
Yeah.
Yeah.
So the required pull is less.
Is more.
So I think there's more pull, but the required pull is less. But now we're making a gravity argument about how much the moon. We're making a gravity and inertial argument, not a bulge argument.
Right, and the inertial argument was also supposed to be wrapped up in the inertial argument.
Exactly.
And you're right. It is a tiny bulge, but it bulges. Like you go to the ocean, you feel it, but somehow it stops.
Right, it somehow stops. And it's only like a meter or two.
Yeah.
It's not. So this meter or two bulge is like, I'm stopping at a meter or two. Stopping.
Yeah, why not 3 or 4?
Why not 3 or 4? Like, how do we predict? I guess that's might be the next part. It says predicting the size of the bulges. Maybe the bulges grow
until it becomes too hard, and then it breaks.
And it breaks.
Splash, splash all over the place.
Maybe we do that next time. Because I still can't put it together.
Thought we had it.
This is a much better model than previous things we've read. Yeah.
The vectors helped.
Vectors helped.
All right. Continue next time.
All right. Continue next time.